Hi, everyone. My name is Edwin. I am on the compilers and toolchain team at Revos. We're working on building high-performance RISC V cores. Thank you for coming to this talk about CI and fuzzing for RISC V. So quickly, I'm just going to go over a brief motivation for these projects, and then go into the GCC pre-post commit CI, some dashboards into showing the health of the current RISC V trunk, and also go into the fuzzer. So to understand the motivation, I'm going to go a bit farther back into the GCC 14 release. You don't need to really read through this. The most important thing probably is that auto-vectorization was enabled for RISC V, and a lot of other RISC V vector work also went in. So the problem at that time was that going from GCC 13 to GCC 14 was a really big jump. GCC 13 release had very minimal support for vector. And so getting to where we were in GCC 14 release is quite amazing. But at the time, there wasn't exactly a good automated RISC V testing infrastructure. And there were periods of times where trunk was not guaranteed to even build. The generated code may not be correct, and there was a significant portion of Spec 2017 benchmarks which failed to either compile or produce the correct output. And even during that time, there was potential discussions about having to delay the release of auto-vectorization to the 15 branch due to the state of the trunk. So this kind of led to wanting a way to catch bugs earlier for the maintainers and developers to fix before moving on to something else, and also provide consistent accessible testing environments for RISC V developers. There were plenty of situations where we would encounter bugs only to have a response of, oh, well, we tested it on our system and it didn't work. Additionally, wanted to find some small reproducible bugs that we might not necessarily know about, and hopefully by having these smaller bugs, it could potentially lead to helping our problems with Spec 2017. Because the problem with the Spec 2017 bugs is that it could take a significantly long time to even run. And as a result, if we were able to find a smaller reproducer that we could iterate faster on, it would help tremendously. And so this kind of led us to the development and creation of the pre-post commit CI and also to the fuzzer. So I'm going to talk a little bit about post commit. As the name sounds, we pull from trunk 4 times a day, build it and test it with glibc and ulib, just to test 2 different libcs. And we compare each report to the previous build. So we test 28 different configuration targets, and by configuration targets, I mean different extensions. RISC V is very customizable, very flexible, but as a result, some extensions may be tested more than others. And so we run 28 different configurations across glibc and ulib just to help cover our basis. Additionally, we have some weekly targets where we run the post commit on 14 release, 15 release, just to make sure that any backboards don't happen to break those release branches, as that would be very bad. And we also test a couple of alternative vector configurations, such as those with different vector lengths of 256, 512, 1024 bits, and different vector register groups. Given how we build it 4 times daily, we have a pretty small bisection range, so this helps tremendously with regards to reducing or identifying which commit caused new regression or fix them. So this is just a brief example of what it looks like. It tells you the number of failures that were solved upon which targets, and also which tests were solved. Additionally, we have information as to which regressions are still present on trunk. So on the left shows all targets regressions, and on the right shows target configuration-specific regressions in addition to the ones on the left. So the pre-commit builds upon the post-commit in that we pull from post-commit good baseline hashes. By good baseline hashes, I just mean that it builds and tests properly. This gives us a relatively good comparison point and gives us an idea as to what patch, which patch introduced or solved some regressions. We pull from patchwork, and patchwork essentially grabs patches from the mailing list. We apply those patches, build a test, and report it to patchwork. And the right is the patchwork interface if you're not familiar with that. As of right now, we currently filter based off of RISC V patches. So if the patch itself has RISC V mentioned anywhere, whether it be in the name or you happen to modify a RISC V file, it automatically gets plumbed into the CI. Additionally, people like Richard Biener has used our CI for testing his middle end changes and is just worried something might break on other systems. You could easily get plumbed into the CI by CCing patchwork CI at RISC when you're submitting the patch to the mailing list. Our goal is to provide a pretty fast response time, so we try to get our results within 2 hours after the patch has been received, and this just helps with the development cycle. Similar to post-commit, this is just like an example of what it looks like. We try to make things as user-friendly as possible. We give you previews, which is the tail end of the test suite logs or build logs, and try to make things as user-friendly as possible so you don't have to dig through our artifact system. If these aren't enough, you could always go through and download the artifacts yourselves and parse through the logs, but try to make things as easy as possible. So now going to the dashboards, we have a lot of different dashboards which show the health of the RISC V port. This is just an example of our vector one. This data was taken probably 2 weeks ago. So you could see the total number of failed test cases and also like how many files have a failed test case. This includes everything, scan dumps, and all of that. Given the nature of the development right now, we have a lot of scan dump failures, which just come from all of the churn. And so we have additional dashboards which filter out those scan dump failures. So these are, this shows all of the failures, which are segmentation faults, internal compiler errors, or have like some sort of excess of errors mentioned inside of the Deja GNU test suite. This is just a condensed view, and it should hopefully give a better understanding of how healthy the RISC V port is. So now, very quickly, I'm going to talk about the fuzzer. If you're not familiar about what a fuzzer is, it's just a random number, gets into the fuzzer, outputs a C program. We run the C program against RISC V and x86 and compare the outputs. We basically built a tool chain and put it through C-Smith and YARPGen and fuzz on master and LLVM. Overall, throughout the times, we've had over 100 GCC finds, probably over 100 LLVM finds, and we still are generating interesting test cases to this day, even though some might be duplicates. But duplicates are good in the sense that they do give us more confidence that these are real bugs. So finally, I'm just going to, in the interest of time, leave at this graph. We could kind of see, since this project started in late 2023 to the GCC 14 release branch, we had submitted close to 50 bug reports. And these are bug reports that helped improve the health of the RISC V port. It helped make sure that these test cases are not actually encountered in the wild by end users. So very quick shout out to RISC V software ecosystem, their RISE. They help us with compute resources and enabling this project to survive. And so thank you.